Please title these notes Limits 3 Notes, Vertical Asymptotes, and Limits as x approaches infinity. By the end of this lesson, you should be able to use algebra to find limits in two of the other situations we were looking at in Limits 2. That was this one, when we have non-zero number divided by 0, that's vertical asymptotes, and then as x approaches infinity. So when we look back at this, we got to remember our plan from Limits 2, which is our first try is just always going to be to plug in this number right in for x, because if it works, then that's all we have to do. We're done. We've got a continuous function. We're happy. So let's try that. We've got 2 divided by 3 minus 3. That's 2 divided by 0. No luck in terms of getting a finite number because we're not allowed to divide by 0. But what we can do is we can look at this and we can say we know that a finite number over 0 means there's a vertical asymptote at x equals 3. Look back at Limits 2 notes if you're confused about why that's the case. So, our possible limits are plus or minus infinity or does not exist. The reason we have a vertical asymptote at the value that makes the denominator 0 is that as we put in denominators that are closer and closer and closer to 0, so let's say 2 divided by 0.1, 2 divided by 0.0001, 2 divided by 0.000001, and so on and so forth, you can see that as the denominator gets smaller and smaller and smaller, the number itself, the value, gets larger and larger and larger and larger. And if we do the same thing except with negatives, so 2 divided by negative 0.1, 2 divided by negative 0.0001, 2 divided by negative 0.000001, we can see that these numbers are getting more and more and more and more negative. We know that we can never have a value at that number that makes the denominator be 0, and you can never have a value for y because we're not allowed to divide by 0. So basically what we see is that as we sort of get closer and closer to it from each side, either the value is getting closer to positive infinity or to negative infinity, and that's what creates that vertical asymptote there. So we're trying to find an overall limit. That means we have to find the left and the right limit, just like we have before. Let's start with the right limit. Excuse me, that's the left limit, that negative. So the left means we're coming from this side. So this number here is going to be a number slightly less than 3. So a number like 2.9 or something like that. And it's not that we're figuring out the numerical value of this when x is 2.9. We simply need positive or negative because we know our answer is positive or negative infinity. We just need the sign. Is it positive or negative? So 2 is a positive. And if we put in 2.9, 2.9 minus 3, that's a small negative. And what's happening is as we get closer and closer to 3, we're going to have 2.9, 2.99999, 2.9999999, etc., etc. We're getting closer and closer to 3. But because we are inherently coming from the left, all of those numbers are going to be at least a tiny little smidgen smaller than 3. So no matter how small this gets, this denominator, it's still going to be negative, and that's what we need. So a positive number divided by a small negative number, whether it's small or not, is going to be a negative. And because it's some finite number, and it's being divided by a very, very, very small negative, it's just like what I was showing on the calculator. It's going to end up being a very infinitely large negative number. So when we do the same thing with the right limit, because we know that we're in this vertical asymptote situation, this number, because we're coming from the right, is going to be a number slightly greater than 3, like, let's say 3.1. So what we have 2 is going to be positive. And then if this is 3.1, 3.01, 3.00001, whatever, as long as it's coming from the right, it's going to be a little bit bigger than 3. So that it minus 3 is going to give us a very small positive. Positive divided by a positive is positive, and a number divided by a very, very small number is going to be infinity. Notice, though, that the limit as x approaches 3 from the left does not equal the limit that's negative infinity, that's positive infinity. So the overall limit does not exist. Okay, let's do some more practice with those ones. Pretty much all of these in the vertical asymptote section are basically the same. We just need to figure out what the sign is, and it's positive or negative infinity. Going to find the limit as x approaches negative 5 of x plus 11 over x plus 5. And again, our first step is to try to plug these in, see what we get. So negative 5 plus 11 over negative 5 plus 5, we've got 6 over 0. So that means we have a vertical asymptote. So the limits must be positive or negative infinity, or does not exist. And so to figure out which it is for the overall limit, we need the limit as x approaches negative 5 from the left, and also from the right. So we're approaching from the left, so x is going to be slightly less than negative 5. And that's going in both these spots. Negative 5.1-ish plus 11, that's going to be still positive, because 11 is way bigger. And negative 5.1 plus 5, that's negative, so we're going to have a small negative. Positive divided by negative is negative. A number divided by a very, very small number is infinity. Here, similar idea. We're approaching from the right, so that means that x is going to be slightly bigger than negative 5. Like negative 4.9 or thereabouts. Remember that when we're in the negative numbers, negative 4.9 is bigger than negative 5 because it's to the right. So a negative number, negative 4.9 plus 11, 11 is way bigger, so it's still going to be positive. Negative 4.9 plus 5, that's also a positive number, so down here is a very small positive. Positive divided by positive is positive. A number divided by an extremely small number approaches infinity. Again, overall limit does not exist, because this is negative infinity, this is positive infinity, they don't match. So let's look at an example where they do match. Find the limit as x approaches 2 of negative x over x minus 2 quantity squared. So first thing we plug in, make sure it's to both x's. Yes, we do have to plug in every time because while in this unit you know what the outcome is going to be, or in this lesson, excuse me, you don't know when you're doing the actual problem. You have to figure out which of these strategies to use. 0 squared is just 0, so that means we've got a vertical asymptote. The limit must be positive, negative, infinity, or it does not exist. So to figure out the overall limit, we do the limit as x approaches 2 from the left. We're approaching from the left, so that means that x is slightly less than 2, such as 1.9. And when we do that, we put the 1.9 in for both of the x's. Negative 1.9 is going to be a negative. Here, 1.9 minus 2 is negative, but the whole thing is squared. So a small negative squared is going to give us a negative over a small positive. So when we divide those, we have negative, a number divided by a very, very small number, infinity. Let's look at the same thing from the right so we can find the overall limit. We're coming from the right, so that means x is slightly more than 2, like let's say 2.1. So negative 2.1 would still be negative. And 2.1 minus 2 would be a small positive, but it's squared, so it's still a small positive. So exactly the same as it was up here. Negative divided by a positive is negative. Number divided by a small number is infinity. So now, in this case, these two match. The overall limit as x approaches 2 is negative infinity. Just going to write why that is. They match. So overall limit exists. In all of these problems, x has been approaching a number, and the limit has been negative or positive infinity. In the next set of problems, we're going to look at x is approaching infinity and see what happens when that occurs. So label these limits as x approaches infinity. And basically what happens, so if we think about our little xy axes, we kind of have a couple of options. One is that the curve could sort of go off up to positive infinity. Another is that the curve could go down to negative infinity, or it could sort of flatten out into a horizontal asymptote. These are sort of the three options that we have. The limit could be positive or negative infinity, or it could be some particular finite number. So the problem with this is that infinity isn't really a number. We can't really plug it in the way that we've previously done with numbers. However, we can plug in larger and larger numbers for x to find the limit as x approaches infinity. Basically, what would it want to be if it was possible to plug in infinity? That's going to give us a couple of rules. Let's first write So to do that, we need sort of some infinity rules. First, a very large number times any other number is still a very large number. Large, I mean in magnitude, so it could be either very, very positive or very, very negative. And in fact, the rules for multiplying positives, and negatives hold regardless of how big the numbers are. Which is kind of cool when you think about it, because like 1 plus a super huge number, like we don't care about the 1. It's just too small to even pay attention to. But -1 times a very, very large number shifts the sign. This little tiny -1 can do this massive change even to this really huge number, which I think is pretty cool. One other rule is the one we were working with earlier. A number divided by a very small number approaches positive infinity or negative infinity depending on the signs of the number. And then our final one is the really critical piece for the rest of this. A number divided by a very large number approaches 0 regardless of the signs of the numbers. So where this one's going, is if I take, let's say, 1 divided by 10, and I start getting bigger and bigger and bigger, that's just move the decimal point 4 places to the left, so that's close to 0. That's even closer to 0, and so on and so forth. The bigger the number is in the denominator, the smaller the number is overall. This is true even if I have 1 divided by, let's say, negative 100. It's still a negative number, but there are so many zeros, we almost don't care if it's negative. It's just so close to 0. So this is the key one for what we're about to do next. Oh, there is one other key piece. When we are working with very large numbers, approaching infinity, the terms in the numerator and denominator that have the largest exponent overwhelm all other terms. Basically, let's imagine we had a number like, 100 million or something like that. 100 million to the 5th power is such an enormously huge number that it completely overwhelms even 100 million to the 4th power. Because 100 million to the 4th power is really, 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 really huge, but 100 million to the 5th is 100 million times bigger. And it's so much bigger that we can essentially ignore even a number like 100 million to the 4th. Even though that's huge, it pales in comparison. It's kind of like saying, an elephant is really, really big, but when you compare an elephant to the size of like the entire planet, the elephant's so small you can basically ignore it. So let's look at some examples. Let's find the limit as x approaches infinity of 3x squared plus 5x over 15x plus 2. And what we were just talking about right here is saying that when we look at this 3x plus square plus 5x, if we're dealing with numbers like 100 million, a quadrillion, a billion, 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 close and closer and closer to infinity, this square term is so huge that this one we can basically ignore. The same thing here. This term gets so huge that we can basically ignore this too. So this behaves like, I'm just going to circle those big exponents. Behaves like that. Now notice I am not saying it equals because it doesn't equal. I'm saying because x is approaching such a large number, we can kind of ignore these for practical purposes. The effects of these other terms get so overwhelmed. But it is really important. This behaves like, it's not that these two are equal, because we just took these out. We aren't allowed to just take out random things, except that for practical purposes, these two parts are overwhelmed and we can ignore them. Once we have this, we just simplify it. Once I've gotten past this part, this is equal to what I'm about to do. So the x's cancel out, 3's cancel out, so we have x over 5. And the thing is, this is 1/5 times x. As x gets to be a really, 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 really big number, even if we're multiplying by 1/5, it's still a really, really, really big number. So as x approaches infinity and gets bigger and bigger and bigger, x divided by 5 continues to get bigger and bigger and bigger. It approaches infinity. So for this one, we find the biggest exponents in the numerator and denominator, so they overwhelm everything else. So this behaves like the limit as x approaches infinity of 3x over 5x squared. So those x's would cancel out, so that would be the limit as x approaches infinity of 3 over 5x. Now, look back at what we were saying here. A number divided by a very, very large number approaches 0. So as this gets bigger and bigger, 3 minus 500, 3 minus 500,000, 3 minus 500 million, zillion, quadrillion, billion, this is getting to be a finite number divided by an incredibly huge number. And when we divide by a very large number, that limit, that's approaching 0. Very, very key. People like to forget this one a lot. What can also happen is we can have situations like this. They're our biggest exponent. So this behaves like notice how in this case, oops, there's the example. Notice how in this case, x to the 5th and x to the 5th cancel out. Because no matter how big they are, they're always equal. And anything divided by itself is 1. It just always is, even if it's 10 million, quadrillion, billion. Now, when we go to put our large number in and see what happens, there is no x anymore. So, since we can't put this in, all that we have is 4/3. The limit is just 4/3. And what this is really saying is it's really saying that when we would draw the graph, there is a horizontal asymptote at y equals 4/3. This one actually is also a horizontal asymptote. Y equals 0. All that's saying is it's saying that as we draw our graph, there we go, that's the second one right here. As x gets bigger and bigger and bigger, y is getting closer and closer and closer to 0. It's just leveling out at that horizontal asymptote. We can also end up with limits where the sign changes. So the limit as x approaches infinity of negative 3x to the 5th plus 7x to the 4th over 2x cubed plus 9. So the biggest exponents here behaves like bunch of canceling out is going to happen. Negative 3/2, that's x squared. So what's happening is that this x squared, as we approach infinity, it's a bigger number, so we're getting one of the infinities. But because there's a negative, it's going to be a positive times a negative, or a negative infinity. We can also work with problems where we are taking the limit as x approaches negative infinity. Same idea, it's just we might have a different sign. So let's say our function is 4x to the 4th plus 7x squared minus 2 all over 6x plus 1. That means these are our terms for the biggest exponents. Oops, this up here should have been the limit as x approaches infinity for that one. So that would be the limit as x approaches infinity of 2/3 x to the third. This is negative infinity, my bad. So as we put negative infinity in, a negative cubed is still going to be a negative, times a positive is still a negative. But this infinity cubed is going to be huge, bigger and bigger and bigger and bigger and bigger and bigger numbers. So it's going to be approaching negative infinity. Let's do a couple more just for practice. It's going to approach negative infinity. These are the terms of the biggest exponents. Those x to the thirds cancel out. There's no x to plug any numbers in for, so just 7/3. Again, that's going to be that horizontal asymptote. And for our final example, let's do another one with a asymptote. Largest exponents behaves like we're going to be dividing by a very, 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 very large negative number. It's going to be squared, so it'll eventually be positive. But anyway, a very, very, very large number up here, down here. Regardless of the sign, a number divided by a very, very large number approaches 0 as that number gets larger. This is one, again, very, very easy to forget. Okay, there's one final problem type that I want to show you, and then we're done. These are tricky problems. A function f of x has a vertical asymptote at x equals 5 and a horizontal asymptote at y equals 4. What could be the values of the constants a and b if f of x equals ax squared plus 9, that's an a, that's a 9, over x squared plus b. So let's think back to what was going on in this lesson. So when we first started out, we knew that we get a vertical asymptote here at x equals 3 because when we plug it in, we get a finite number, non-zero number, divided by 0. I should say finite non-zero. So what that means is it means here, if this whole thing, if we have division by 0, then that means that we would have a vertical asymptote there as long as this wasn't also 0. So a vertical asymptote occurs when the denominator is 0, but the numerator is not. So when x equals 5, because it says there's a vertical asymptote at x equals 5, the denominator, x squared plus b, should equal 0. So put the 5 in, so 5 squared plus b equals 0. B equals negative 25. If we look up here, there's very little danger when we put in 5 squared times a plus 9. We'll have to keep an eye on what a ends up being, but it's probably unlikely that when we put 5 in, we're also going to get 0 up in the numerator. So similarly thinking, we get a horizontal asymptote. We got that out several times here. And we got that when the limit as x approached infinity was a particular number. So let's go and find the limit of this as x approaches infinity. So these are the two biggest exponents. So this is going to be behaves like the limit as x approaches infinity of ax squared over x squared. Those cancel out. So that means that we have a vertical or horizontal asymptote at y equals a. The problem tells us that we have a horizontal asymptote at y equals 4. So if y equals 4 and y equals a, then a must equal 4. Now let's look back. If we put 4 in for a and 5 in for x, is this numerator going to be 0? Clearly not, because that's going to be positive. Positive is going to be very positive. So that's okay. This is still going to create a vertical asymptote. This concludes the notes for limits 3.